This is William Michael of the Classical Liberal Arts Academy, and in this video, I'd like to begin helping students in the Classical Liberal Arts Academy who are working through high school physics. As I get started with this, you may wonder, what in the world is a classicist doing teaching a physics course? And I would have you know that I started studying classics in college after I had already begun studying as a pre-med student. I was a Dean's List pre-med student at Rutgers University. I was studying and preparing to go to medical school. I was a good student in the natural sciences, but I became interested in philosophy and classical languages as I matured as a Christian and chose not to continue, not to pursue modern sciences. But I worked in a chemistry lab while I was in college, enjoyed studying the natural sciences, and am very comfortable teaching high school level physics and chemistry, biology, and so on. So I'm not entirely ignorant of these subjects, and I enjoy the opportunity. I look forward to the opportunity to work through these studies with Catholic students in the academy because these studies in modern natural science require some criticism. They need to be studied with a critical spirit. In fact, I would say the whole point of the scientific method and modern science is to question and to test things that are stated about the natural world. And so I think there's a tendency for students and teachers in the modern natural sciences to say that they're all about testing things. But then when it comes time to actually study, there's not much testing, there's not much criticism, there's not much questioning. We get this textbook study where we're just drinking in all kinds of statements and information without actually asking, are these things true? So I'd like to go through this widely respected modern physics textbook with students in the academy, learn the content of this book as well as we can, but also take some time to ask some questions and make sure we're not just memorizing things that we should actually be questioning and testing and so on. That's the real spirit of the modern natural sciences and the scientific method. So what I'd like to do is simply read through this textbook for students and comment here and there to try to make things as clear as possible. I'd like to do this for a couple different reasons. First of all, I'd like to provide students with instructional time. To put a physics course on a high school transcript with one high school credit, which is what a high school student should be working to do, it's assumed that that one high school credit means that the student has received 120 hours of instructional time. So in these videos, as we go through this book, I'd like to actually provide that instructional time for students so there's no confusion about your high school physics studies. There's no uncertainty as to whether or not you've covered what needs to be covered or whether you've had enough time, things like that. So by just going through the book together, discussing it, asking me any questions that come up along the way, and communicating with me will allow you to easily fulfill those requirements for 120 hours of instructional time. And we'll just work through the textbook together. So I'd like to ask you through these videos to carve out some time, about an hour for each video. Have a notebook with you to jot down some notes. And remember, the purpose of note taking is not just to summarize the content of what you read, it's also to jot down your own thoughts, things that come to mind, interesting questions that you have as you study any subject. Your notes are a summary, that's true, but they're also a journal of your own thoughts, questions, your own new discoveries, and so on as you go through your study. So keep a notebook open, keep a pen in hand. You can hit pause at any time. You can back up and re listen to anything that you miss. So just make good use of these videos. Enjoy the study time together. Ask any questions you have, and we'll fulfill the requirements for high school physics. So we're going to jump right into this first chapter. We see the title here, What is Physics? And if we look down to this chapter outline, we see in this first chapter, there are 3 sections. In the first section, we're going to look at definitions and applications in physics. In the second section, we're going to look at the scientific methods, and notice that method is plural there, the scientific methods. And then in the third section, we're going to look at the language of physics, physical quantities and units. This is a pretty lengthy chapter with lots of information, so we're just going to take our time and work through it. We're going to read the text together. I'll make some comments that I think will be helpful, and we'll just make our way through and take whatever time we need. So follow along. Feel free to hit pause at any time, take a break, stretch, go for a walk, get a drink. But let's work through all of this text together and learn what we can of the modern science of physics. So let's get started with the lesson here. First, there's this brief introduction, then we get to section 1.1, which is this first section in the outline here. Take a look at the image above of the Andromeda galaxy. So we've got this image of the Andromeda galaxy in outer space. It contains billions of stars. This galaxy is the nearest galaxy to our own galaxy, which is called the Milky Way, but is still a staggering 2.5 million light years from the Earth. A light year, if you don't know, oh, never mind, it actually tells us in the next sentence here. Let's keep reading. A light year is a measurement of the distance that light travels in 1 year. So think about what a great distance that is. The speed of light is almost impossible for us to notice. It moves as fast as we can even imagine. And light speed, or a light year, is the distance that light travels in an entire year. So imagine what an incredible distance that is. And this Andromeda galaxy is said to be 2.5 million light years away. So that's the distance light would travel in 2.5 million years. Despite this, the primary force that affects the movement of stars within the Andromeda galaxy is the same force that we contend with here on Earth, namely gravity. And I'd like you to have a critical mind as you read this. We're seeing many assertions being made here with no evidence. So we're reading this and we're giving the author the benefit of the doubt to some degree, but at some point, we're going to have to ask for some evidence. How do we know gravity actually exists? How do we know gravity is the best way to explain this force that we claim to observe? How do we actually know how fast light travels in a year? There are many questions that we can ask even as we get started here. And at some point, like I said, we can give the author the benefit of the doubt for now. But at some point, we're going to need to see some evidence. So let's keep a critical spirit, learning what we can, working to understand the author's message, but also keeping note of the fact that we're receiving lots of assertions about the natural world for which we're not being provided any evidence. So we want to see what that evidence is. You may soon realize that physics plays a much larger role in your life than you thought. This section introduces you to the realm of physics and discusses applications of physics in other disciplines of study. It also describes the methods by which science is done and how scientists communicate their results to others or to each other. In this last paragraph, we just have a summary of these 3 sections in this chapter. So that's our introduction. And the idea there is that physics is a study of the natural world, of how things work, why things do what they do in the natural world. And obviously, as we're living creatures moving around, doing all sorts of things, influenced by all of the things around us, if it's true that we can understand what causes things to do what they do, obviously that knowledge is very important to us. So this is what we're going to be pursuing in the study of physics. So let's go ahead and jump into the first section here. We have a list of objectives which we want to read because this tells us what our goals are for this first section. By the end of this section, you will be able to do the following. You will be able to describe the definition, aims, and branches of physics. By the end of this section, you will be able to describe and distinguish classical physics from modern physics and describe the importance of relativity, quantum mechanics, and relativistic quantum mechanics in modern physics. You will be able to describe how aspects of physics are used in other sciences like biology, chemistry, geology, and so on, as well as in everyday technology. So these are the objectives of our study in section 1.1. Now, you may not know what any of this stuff means, and that's okay. Notice it says by the end of this section. In other words, we're going to learn and discuss these things in this section. And we'll come back and check and see how we're doing when we finish. Now, in this section here, in section 1.1, we're told that there are some key terms to watch out for. And if you're taking notes, I would encourage you to write these terms down in your notebook and keep an eye out for them as we study. The first term is the atom. The second term is physics. Then we have classical physics, modern physics, quantum mechanics, and the theory of relativity. So we'll keep an eye out for these important terms in this section. To get started, let's learn what physics is. What physics is. You can see in bold here, we have the term physics. So we want to have an accurate understanding of what physics is. What does this textbook actually mean when it uses the term physics? If someone says, "Have you studied physics?" what does that actually mean? Aristotle wrote a book titled Physics back in 350 BC. Albert Einstein studied physics in the 20th century. Did they study the same thing? Did they mean the same thing by the word physics? Let's learn what this word physics means, at least in this textbook. Think about all of the technological devices that you use on a regular basis. Computers, wireless internet, smartphones, tablets, global positioning system, or GPS, MP3 players, satellite radio, all of these might come to mind, and many others. Next, think about the most exciting modern technologies that you have heard about in the news, such as trains that levitate above their tracks, invisibility cloaks that bend light around them, and microscopic robots that fight diseased cells in our bodies. All of these groundbreaking advancements rely on the principles of physics. Physics is a branch of science. Physics is a branch of science. The word science comes from a Latin word that means having knowledge, and it refers the knowledge of how the physical world operates based on objective evidence determined through observation and experimentation. So, this word science, we've got something of a definition here. We read that science refers to the knowledge. So, science is a kind of knowledge of how the physical world operates. Notice it's not knowledge of how the spiritual world operates, not knowledge of how God operates, and so on. It's a knowledge of how the physical world operates based on objective evidence determined through observation and experimentation. In other words, it's not based on reasoning, it's not based on faith, it's based on what we can actually observe. And this is why it's so important, as I said before, that anything that anyone says to us in the name of modern science must come with objective evidence. So we can't say, well, this is what everybody believes today, or this is what scientists think, or this is what. No, science is knowledge based on objective evidence, determined through observation. That means that we can see it, feel it, smell it, taste it, etc. And experimentation. That means we can reproduce the experiences and experience them for ourselves. Anything that doesn't meet that description is not rightly called science. And I would argue that much of what we hear in modern society in the name of science does not meet this description. And that's what I would like for you to watch out for. Okay? A key requirement of any scientific explanation of a natural phenomenon, something that takes place in nature, is that it must be testable. It must be testable. So, for example, when scientists talk about how the world began, we can only accept something as a scientific explanation if it's testable. If it is not testable, then it is not scientific. If it's not testable, then it's not scientific. And I want you to be critical in these things, not because I want you to reject modern science or ignore modern science, but to be a great modern scientist, to be a real scientist, you've got to stick to these definitions. If you don't stick to these definitions, you will not actually be a scientist. So it's for the sake of science, it's for my respect for science that I hold scientists and science teachers and anyone around me who speaks about scientific things. I hold them accountable to these definitions because much of what is said about science today is not scientific. Let's commit to being true scientists. And if we speak of scientific things, let's make sure that our scientific explanations are testable, that they're determined through observation and experimentation, that they're restricted to the physical world, and so on. These are the requirements of real science. One must be able to devise and conduct an experimental investigation that supports or refutes the explanation. It is important to note that some questions fall outside the realm or reach of science because they deal with phenomena that are not scientifically testable. This need for objective evidence helps define the investigative process that scientists are supposed to follow. Not all scientists. We should say the process that true scientists follow, which will be described later in this chapter. That's a very important paragraph right there. I would encourage you to read that again and again and again. Very important. Physics is the science. Let's learn about physics specifically. Up here we learned about science in general. Let's get to physics in particular. Physics is the science aimed at describing the fundamental aspects of our universe. This includes what things are in our universe, what properties of those things are noticeable or observable, what processes those things or their properties undergo, what changes they undergo. In simpler terms, physics attempts to describe the basic mechanisms that make our universe behave the way it does. So there you have a good definition or description, at least, of what physics is. We learned up here, physics is a branch of science. That means that physics always has to follow these rules for what true science is. And we see here that physics attempts to describe the basic mechanisms that make our universe behave the way it does. Physics seeks to understand and explain why things in our universe do the things that they do. And you can imagine how helpful that knowledge can be. For example, consider a smartphone. Physics describes how electric current, how electricity interacts with the various circuits inside the device. This knowledge helps engineers select the appropriate materials and circuit layouts when building a smartphone. Next, consider a GPS. Physics describes the relationship between the speed of an object, the distance over which it travels, and the time it takes to travel that distance. When you use a GPS device in a vehicle, it utilizes these physics relationships to determine the travel time from one location to another. So again, the key in that paragraph is understanding what physics seeks to do. Physics attempts to describe the basic mechanisms that make our universe behave the way it does. It's worth noting that if the physics are wrong, if our understanding of these mechanisms is wrong, then our smartphones will be wrong. Our GPS devices will be wrong. So we can see the importance of understanding the science and constantly testing the science is because just because our clock says this or our GPS device says this, if those devices are based on principles that are not actually true, they themselves will give us false results. So there's always room for improvement, there's always room for testing, and so on. And that's really what we seek to do through the knowledge of physics. As our technology has evolved over the centuries, physics expanded into many branches. Ancient people could only study things that they could see with the naked eye or otherwise experience without the aid of scientific experiment. Notice that's an assertion being made about ancient people, that they only studied things with the naked eye and that they didn't have any scientific equipment. We should ask whether that statement is actually true. Maybe they had different kinds of equipment. Just because they didn't have electronic equipment doesn't mean they had no equipment. Maybe they had other ways of observing the natural world. So watch out for judgments like this that make us think ancient people were somehow stupid or that they didn't understand as modern scientists can understand. That's not necessarily true. This included the study of kinematics, which is the study of moving objects. For example, ancient people, the author says, studied the apparent motion of objects in the sky, such as the sun, moon, and stars. This is evident in the construction of prehistoric astronomical observatories, such as Stonehenge in England. Notice the author is asserting that Stonehenge, which we see here in this picture, was an astronomical observatory. That's a statement that the author has not proven. So we're being asked to trust that the author's statement here is true, and that's not a very scientific thing to do. So this is why I say we've got to learn to read modern science critically and carefully. I'm not saying he's wrong, but I'm saying he's making assertions without evidence. Ancient people also studied statics and dynamics, which focus on how objects start moving, stop moving, and change speed and direction in response to forces that push or pull on the objects. This early or ancient interest in kinematics and dynamics allowed humans to invent simple machines, such as the lever, the pulley, the ramp, and the wheel. These simple machines were gradually combined and integrated to produce more complicated machines such as wagons and cranes. Machines allowed humans to gradually do more work, more effectively in less time, allowing them to create larger and more complicated buildings and structures, many of which still exist today from ancient times. So notice that simple machines were simply combined to produce more complicated machines. So we can look at complicated machines and say, oh, this is much better than what they had in the ancient world, but it's simply a combination of the simple machines which we would expect to develop over time. It's not that the moderns are more advanced or more intelligent, they simply live after the ancients and benefit from their discoveries. So we've got to be careful in the criticism of the ancients. Often the beginning is the most difficult and challenging part of a work. So just because the ancients developed the simple machines and moderns may have complicated machines, that doesn't mean the moderns are smarter or have a better understanding of the truth than the ancients did. So we need to be careful that we don't look at the ancients in a prejudicial way and assume that because they didn't have what we have, that they were dumb, because that's not true, as we'll see when we study not just science, but also philosophy and history. Machines allowed humans to gradually do more work effectively in less time. So they improve the efficiency of our work. They improve the size of buildings, the complexity of buildings and structures. And many of the things that were developed by the ancients still exist today. So we can't criticize the work that they did. They may have done it differently, they may have done it more simply, but things like Roman roads, Roman aqueducts, the pyramids of Egypt, they're incredible structures that even modern scientists have a difficult time explaining how they were made by the ancient peoples. As technology advanced, the branches of physics diversified or separated even more. These include branches such as acoustics, the study of sound, optics, the study of light. In 1608, the invention of the telescope by a German spectacle maker. A spectacle maker means a lens maker or a maker of glasses. Hans Lippershey, I'm guessing at that pronunciation there. The invention of the telescope led to huge breakthroughs in astronomy, which is the study of the objects or phenomena in space. So when we ask why was there reportedly a breakthrough? It was because technology improved. A German spectacle maker invented the telescope. 1 year later, in 1609, Galileo Galilei began the first studies of the solar system and the universe using a telescope. During the Renaissance era, Isaac Newton used observations made by Galileo to construct 3 laws of motion. Notice it says his 3 laws of motion. So based on his studies, Isaac Newton published teaching about the 3 laws of motion in the natural world. These laws were the standard for studying kinematics, which we learned about a few paragraphs above, and dynamics even today. So that was back in the 1700s. Another major branch of physics is thermodynamics, which includes the study of thermal energy and the transfer of heat. And the word thermal has to do with heat, the energy of heat and the effect of heat. James Prescott Joule, an English physicist, studied the nature of heat and its relationship to work. Joule's work helped lay the foundation for the first of 3 laws of thermodynamics. 3 laws of thermodynamics, don't get that confused with Newton's 3 laws of motion, 2 different things. These are the 3 laws of thermodynamics that describe how energy in our universe is transferred from one object to another, or is transformed from one form to another. Studies in thermodynamics were motivated by the need to make engines more efficient, to keep people safe from the elements, that is, from the natural world, and to preserve food. There's a saying that necessity is the mother of invention, that the inventions of men are brought about by necessary things in life, and we see a good example of that here. Studies in thermodynamics were motivated by simple necessary problems. We needed to make engines more efficient. We needed to keep people safe. We needed to preserve food. So you see how basic needs, simple human needs, lead to studies in sciences where we seek to find solutions to problems. That's why there will always be a need for new scientists. There will always be new problems, new circumstances, and a need for new solutions to be found by new scientists. The 18th and 19th centuries, the 1700s and 1800s, saw great strides in the study of electricity and magnetism. Now, notice we live after these dates. We live in the 21st century. We live in a generation where we're watching the development of electric cars. In the 18th and 19th centuries, electricity wasn't even understood yet. There was no electricity in houses or anything like that, no electric lights. Scientists were just developing their understanding of electricity and of magnetism. Electricity involves the study of electric charges and their movements. Now, ancient people knew about electricity because they saw lightning when there were storms. They saw lightning and understood this concept of electric charges and the movement of electricity. There are also electric eels. They're sort of a fish. It's sort of a fish that it's in between a fish and a snake. But there are eels called electric eels that give off electric shocks as a way of protecting themselves. And even in ancient times, men experienced the shocks that came from electric eels. So the concept of electricity was known, but there just was no motivation at the time to pursue those studies because other things were considered greater priorities. But in the 18th and 19th centuries, there was great interest in electricity and magnetism, and the scientists devoted their attention to these studies. Electricity involves the study of electric charges and their movements. Magnetism had long ago been noticed as an attractive force between a magnetized object and a metal like iron, or between opposite poles of two magnetized objects. People observed these things even in ancient times. In 1820, the Danish physicist Hans Christian Ørsted showed that electric currents create magnetic fields. In 1831, about 10 years later, the English inventor Michael Faraday showed that moving a wire through a magnetic field could induce or bring in an electric current. These studies led to the inventions of the electric motor and the electric generator, which revolutionized human life by bringing electricity and magnetism into our machines. So the 18th and 19th saw the development of the study and use of electricity and magnetism. The end of the 19th century, that is the end of the 1800s, saw the discovery of radioactive substances by the French scientists Marie and Pierre Curie. Nuclear physics involves studying the nuclei, that's the plural of nucleus, the study of the nuclei of atoms, the source of nuclear radiation. Now, I just want to say, we may be reading about all sorts of ideas that you may not be familiar with, and that's okay. Notice what the author is doing here in this section. He's simply giving us a historical overview of the development of the sciences and showing how they developed step by step based on changing needs, based on the discoveries of different scientists, based on the development of different tools and instruments to give us an understanding of how science has developed. So don't think you should understand all of the things that are being described like radioactive substances and nuclear radiation. Just understand the author is giving us a history of the development of the sciences here. In the 20th century, the 1900s, the study of nuclear physics eventually led to the ability to split the nucleus of an atom, a process that is called nuclear fission. So nuclear fission simply means the splitting of an atom, the nucleus of an atom. This process is the basis for nuclear power plants and nuclear weapons. Also, the field of quantum mechanics, which involves the mechanics of atoms and molecules. So notice, quantum mechanics refers to the mechanics of microscopic or even submicroscopic, things that can't even be observed. The study of the mechanics of really what are invisible bodies that are almost known only by theory and not by experience at all, which raises some interesting questions about science, right? Whether these things can be considered scientific. After all, small objects that we can't see are just as much outside the realm of science as distant bodies in the heavens that we can't see. They're essentially invisible. The field of quantum mechanics, which involves the mechanics of atoms and molecules, saw great strides during the 20th century as our understanding of atoms and subatomic particles, that means bodies that are even smaller than atoms, even lower than atoms, our knowledge of these things increased during the 20th century. Early in the 20th century, in the early 1900s, Albert Einstein, who just about everyone has heard of in modern society, Albert Einstein, revolutionized several branches of physics, especially relativity. Relativity revolutionized our understanding of motion and the universe in general, as described further in this chapter. Now, in the 21st century, physicists continue to study these and many other branches of physics. So notice we've got a very helpful overview of the history and development of some of the major events and discoveries in physics through the years. A very helpful chapter. It's helpful because as a scientist or as a student of natural science, you've got to know where you are in the history of science. You've got to understand where science has come from, where it is at present, and where it may go in the future. Because if you do become a scientist, you're not going to be a scientist today. You're going to be a scientist in 20, 30, or 40 years from now. So it's very important to understand where science began, how science developed, where the sciences are now, and to try and predict where they might be in 20, 30, 40 years from now. So understanding physics philosophically, understanding physics historically is very important. Many students neglect those sorts of studies. By studying the most important topics in physics, you will gain analytical abilities, the ability to analyze or examine things that will enable you to apply physics far beyond the scope of what can be included in a single book. These analytical skills will help you to excel academically, and they will also help you to think critically in any career you choose to pursue. So the study of the sciences and physics in particular helps to develop in us a scientific spirit, a scientific mind, an analytical mind, a mind that looks for evidence, that tests theories, and also a mind that isn't afraid to propose theories, that isn't afraid to make a suggestion about what the solution to a problem or the answer to a question might be, even before there's evidence. So that scientific mind, that mind that seeks to solve problems by proposing intelligent theories or educated guesses about what the solutions or the answers might be, and then gets to work to put those theories, to put those hypotheses to the test and try to move closer to the solution. That's the spirit of a real scientist. And That mentality, that discipline, will not only help you in the study of the sciences, but in all different areas of life. And so there's a lot to gain through the study of the sciences, not just the knowledge of the sciences themselves. I think that's pretty clear so far what we've studied. So let's move on to the next section. And remember, if you're watching this video going through this with me and there's something that we looked at that wasn't clear, you'd like to go back and review it, you can do that at any time. Just hit pause, back up, play it again, jot some notes down as you see us cover either the names of famous scientists or terms that are in bold. You can take your time, hit pause, take notes, and so on. We'll just keep moving in the video, though, because you're in control of the video and can stop at any time. So let's keep going here. The next section, physics past and present. The word physics is thought to come from the Greek word physis, meaning nature. The study of nature later came to be called natural philosophy. From ancient times through the Renaissance, natural philosophy encompassed many fields, including astronomy, biology, chemistry, mathematics, and medicine. Over the last few centuries, the growth of scientific knowledge has resulted in ever-increasing specialization. That means focusing on smaller and smaller subjects. Ever-increasing specialization. So as our scientific knowledge has grown, scientists have focused on smaller and smaller subjects and branching of natural philosophy into separate fields, with physics retaining the most basic facets. Physics, as it developed from the Renaissance to the end of the 19th century, is called classical physics. Now notice this is a confusing use of the word classical, because normally when we use classical, we refer to ancient Greek and Roman learning or culture. But here, when we hear the word or the term classical physics, notice that we're not talking about ancient times. We're not talking about Aristotle or Pliny or any other scientists like Galen or Ptolemy the astronomer. Classical physics is actually referring to what we might call modern physics of the Renaissance and through the 19th century. So this is very confusing. Make sure you understand what is meant by classical physics. It's like in music. If you listen to a modern radio station, they'll talk about classical music, but that means the music of Bach or Mozart from the 17th, 18th, and 19th centuries. So be careful when they use this term classical for classical physics, don't think that they're referring to ancient Aristotelian physics or the physics that St. Thomas Aquinas taught in his commentaries on the works of Aristotle. Classical physics refers to the study of physics from the time of the Renaissance. That's usually considered to start in the 14th century, the 14th through the 16th or 17th centuries, from the Renaissance to the end of the 19th century. That's the period of classical physics, so you might want to jot that down and keep that in mind. Revolutionary discoveries started at the beginning of the 20th century, in the 1900s. And these discoveries transformed physics from classical physics to modern physics. So we might think of ancient physics as the physics of the ancient Greeks and Romans and Babylonians and Egyptians. We might think of medieval physics as the physics of the scholastic philosophers like St. Thomas Aquinas and St. Albert the Great. Then we've got what we're calling classical physics from the time of the Renaissance to the 19th century, and then modern physics, which doesn't begin until the 20th century or the 1900s. So make sure those terms are clear in your head as you study these things. Classical physics, classical physics is not an exact description of the universe, but is an excellent approximation under the following conditions. So here's an explanation of what's meant by classical physics, or what was believed and taught during that period of time from the Renaissance to the end of the 19th century. There are certain conditions that need to be assumed or accepted for us to respect the teachings of classical physics. Matter must be moving at speeds less than 1% of the speed of light. Secondly, objects dealt with must be large enough to be seen with the naked eye. And thirdly, only weak gravity, such as that which is generated by Earth, can be involved. So notice that classical physics talks about circumstances that are pretty normal. Matter must be moving slowly. The objects that are being dealt with must be visible. And we're talking about gravity as a force in a way or at a scale that's experienced here on Earth. So in those conditions, the teachings of classical physics can be seen as pretty reliable and accurate. And so we can see that there must have been some change later in the 20th century where we began to experience things that moved much faster, closer to the speed of light, where objects became very, very small and could no longer be seen with the naked eye, or where gravity was studied in places where it's far greater than that which is experienced on Earth. And these conditions led to some of the ideas of that modern or that classical period to be seen as not accurate in all circumstances. So we can see classical physics was accurate when these conditions were assumed by scientists, but it seems that these conditions must have no longer been assumed by scientists, but studies began to be conducted that went beyond them, and that led to a need for some additional teachings or changing of the teachings that would accommodate different circumstances, different conditions. Very small objects, such as atoms and molecules, cannot be adequately explained by classical physics. These three conditions, listed up here, apply to almost all of our everyday experience. In other words, classical physics is useful for everyday life. And as a result, most aspects of classical physics make sense on an intuitive level. So if we study classical physics and just examine the teachings of physics by observations in ordinary human life, we'll find that they're pretty accurate and useful. Many laws of classical physics have been modified during the 20th century, resulting in revolutionary changes in technology, in society, and in our view of the universe. As a result, many aspects of modern physics, remember what modern physics means, many aspects of modern physics, which occur outside of the range of our everyday experience, may seem bizarre or unbelievable. So notice that modern physics is said to deal with conditions that we don't normally experience. Now, this raises some interesting concerns, because if you remember, going back to the beginning of this lesson, we said that scientific thinking is based on observation. It's based on experimentation. It's based on testing. It's based on reproducible experiments. What happens when scientists begin to talk about things that almost no one has the ability to observe? What happens when a scientist claims to observe something that no one else has the instruments to observe. You see how we get into some interesting questions in modern science when the observations move beyond the normal experience of men and women, and the normal people in the world can't really be sure that what the scientists are saying is true, and they have no way to observe it or test it. And so we see how this begins to bring the very nature of science into question. Are we supposed to accept things that are claimed by scientists who appeal to experiments or observations that we can't observe for ourselves? It's a very interesting question in the philosophy of science. What is science? What is our responsibility to science when we can't see the evidence? It's a very interesting, very challenging question that I'd like you to keep in mind. Why is most of this textbook devoted to classical physics if we're claiming that modern physics now knows many things that show classical physics to actually not be true? And again, we're assuming that modern physics is itself true. Why is most of this textbook devoted to classical physics rather than, let's say, modern physics? There are two main reasons. The first reason is that knowledge of classical physics is necessary for us to understand modern physics. Knowledge of classical physics is necessary to understand modern physics, just like the study of history is important, necessary to understand the present and the future. The second reason is that classical physics still gives us an accurate description of the universe under a wide range of everyday circumstances. In other words, classical physics is useful. So the two reasons why we're going to study classical physics, even though the author is going to claim that modern physics has replaced classical physics, is that classical physics is necessary to understand modern physics, and classical physics is useful. Modern physics includes two revolutionary theories. So notice that modern physics is based on a couple of radical new theories about the natural world. These two theories are the theories of relativity and the theory of quantum mechanics. Now, notice that these are called theories. We're going to look at this further later on in our study, but it's important to note that they're called theories. Theories are not facts. Theories are answers to questions that are proposed by scientists. Theories are to be tested. So when something is identified as a theory, what that means is it appears to be true, but depends on testing. So modern physics, we're told, includes two revolutionary theories. Make sure you keep that in mind. Relativity and quantum mechanics are theories. These theories deal with very fast and very small. The theory of relativity was developed by Albert Einstein in 1905. And again, notice the theory of relativity. Developed by Albert Einstein in 1905. By examining how two observers moving relative to each other would see the same phenomena. Einstein devised radical new ideas about time and space. And notice the idea is based on this observation. How two people moving differently would observe the same phenomena. So one illustration that's often used, and we'll see this later in the book, is if you're driving down the highway and let's say you're following the sun in the sky or the moon in the sky, you'll notice that if there's layers of trees or any objects between where you are in the car driving on the highway and whatever you're looking at in the distance, you'll notice that it looks like the different objects are moving at different speeds. Things that are close to your sight seem to be moving very quickly, and things that are far away seem to be moving very slowly. But think about what people see who are moving in cars on the other side of the highway, moving in the opposite direction. Things appear to be moving differently to those people. So one person in a car driving south on the highway and another person in a car driving north on the highway can both be looking at the moon. But what they see as they look, what they see, what actually is going on in front of their eyes is not going to be the same thing. And this idea that our observations can be different from one another, especially when we're in motion, that's the idea of relativity. And so Einstein proposed this idea that maybe our movement and the movement of different bodies in the heavens and the fact that all these things are in motion, maybe that causes us to see things from different perspectives. Maybe things appear to be other than they really are. And so this is this idea of relativity. By examining how two observers moving relative to each other could see the same phenomena, Einstein devised radical new ideas about time and space. He came to the startling conclusion that the measured length of an object traveling at high speeds is shorter than the same object when measured at rest. Perhaps even more bizarre is the idea that time for the same process to occur is different depending on the motion of the one who is observing, the motion of the observer. Time passes more slowly for an object traveling at high speeds. Now, notice this is very complicated stuff, and notice again that it's a theory of relativity, and you're not expected to understand all of this as you get started in the first chapter of high school physics. So it's important to learn about these things, to become familiar with the names of the scientists, the names of the ideas that they proposed, because it helps you to see what you need to study in the future. So don't get discouraged or nervous if you don't understand all of this. The author is just presenting you with a history of the development of scientific ideas that show you what's out there to study, that show you what we're going to be studying in physics and why we're going to be studying it. A trip to the nearest star system, Alpha Centauri, might take an astronaut 4.5 years if the ship travels near the speed of light, which it obviously can't. That's a ridiculous idea. However, because time is slowed at higher speeds, the astronaut would age only 0.5 years during that trip. Einstein's ideas of relativity, which are pretty bizarre, were accepted after they were confirmed by numerous experiments. But again, notice that they're referred to as the theory of relativity. We'll also learn about Einstein that many of Einstein's ideas were not actually tested with experiments because many of them are impossible to test. But he used to conduct what he called thought experiments, where he would simply imagine the different things and think of what would happen. So again, we're stuck asking the question, is that really science based on our definition of what science is? Are thought experiments really scientific? So we've got good questions to ask, and that's why I said at the beginning, it's good for us to get into these studies, to learn about these things, to learn about these ideas, but to do so critically with the attitude and spirit of true scientists. And that's what I'd like to help you do. Gravity, which is said to be, notice this is a scientific statement, so let's just be careful here. Gravity is one way of explaining the force that holds us to Earth. Aristotle, for example, had a different explanation for why things stay on the Earth, why we stay on the Earth. Gravity is one way of explaining the idea that there's actually a force that's drawing things, a natural force that's drawing things to the center of the Earth. That's one way of explaining it. But Aristotle had a different way that he explains in ancient physics. So we're assuming this modern idea of gravity. And again, I just want you to be sensitive to assumptions because this is science. Gravity, which is understood to be the force that holds us to the Earth, can also, or is also, thought to affect time and space. For example, time passes more slowly on Earth's surface than for objects farther from the surface, such as a satellite in orbit. The very accurate clocks on global positioning satellites have to correct for this difference in time. They slowly keep getting ahead of clocks on the Earth's surface. This is called time dilation, and it occurs because gravity, in essence, slows down time. Now notice this is a radical, bizarre idea, a difficult idea to wrap our minds around, but it's introducing us to the kinds of thinking and discussions that scientists engage in. Complicated stuff. Large objects like the Earth itself have strong enough gravity or force pulling things toward them to distort space. To visualize this idea, think about a bowling ball placed on a trampoline. The bowling ball depresses or curves the surface of the trampoline. If you roll a marble across the trampoline, it would follow the surface of the trampoline and roll into the depression caused by the bowling ball and eventually hit the ball. Similarly, according to this theory, the Earth curves space around it in the shape of a funnel. Remember, this is a theory. This illustration is not a photograph of the natural world. This is not an observation. This is a theory. The Earth is said to possibly curve space around it in the shape of a funnel. These curves in space due to the Earth cause objects to be attracted to the Earth. That is gravity. Now, my question, for example, just to propose a challenge to this idea, we have this image of the Earth, which is said to be a heavy object like a bowling ball, and we see the space around the Earth presented as the fabric of a trampoline with the Earth pressing down into the center. But one question I have is, what about the space above the Earth? Is that also being pulled downward? And when we think about the Earth, what in the world makes the Earth move downward this way? What is downward? Gravity draws things towards the Earth. What causes the Earth to move downward? So I think that this is a popular illustration and idea that scientists use to explain some observations, but there are reasons why we have to criticize and think carefully about these things, and they have to be subject to questioning. We can't just accept that there's a right answer and pretend that anyone who asks a question is just a crazy person. Remember, people who lived all through history, who discovered things in history, thought everyone before them was dumb, and then they ended up being wrong as well, and that's going to go on and on and on. So we've got to learn to be careful in this arrogance that we have to think that we're right and everyone before us is wrong, and to get frustrated when anyone questions or doubts theories that we propose. I have doubts about the theory that's presented in this illustration. It doesn't make much sense. And I'm going to say that as one who studies philosophy and science, because I would like to see the evidence for this. I would like to know how I can observe this, because that's what it means to be scientific. So don't be afraid to ask for evidence. Don't be afraid to be truly scientific. This isn't religion. We're not being told what's true by God who created the world. This is human science, where humans, based on their own theories, based on their own observations, are attempting to explain things that are very, very difficult to explain. So let's have some respect for the real challenge of science. Because of the way gravity affects space and time, according to Einstein's theory, Einstein stated that gravity affects the space-time continuum. And again, you're not expected to understand all this stuff. This is why time proceeds, or this is an explanation of why time proceeds more slowly at the Earth's surface than in orbit. In black holes, whose gravity is hundreds of times that of Earth, again, according to theory, time is believed to pass so slowly that it would appear to a faraway observer to have stopped. So again, notice in all of this, there are statements made based on assumptions and theories, very interesting, worth listening to and learning about, but at the same time, in need of testing and objective evidence. So let's make sure we commit to be truly scientific and be careful not to just start accepting statements that we have no evidence for. Let's study this as scientists. In summary, relativity says that in describing the universe, it is important to realize that time, space, and speed are not absolute. Instead, they can appear different to different observers. That's what it means to be relative. Time, space, and speed, according to Einstein, may not be absolute. They may not be the same for everyone. They may appear to be different to different observers. Einstein's ability to reason out relativity is even more amazing because we cannot see the effects of relativity in our everyday lives. Now, that may be interesting, but for it to be scientific, remember, there has to be objective evidence. So this may be a very interesting theory. It may be an effective theory that explains how many things appear. But for anything to be truly scientific, it has to have objective evidence, and it must be testable. We saw that earlier in the chapter. So we've got to be very careful when we get into these theories about things that we can't actually and don't actually observe. Now that was about relativity. Now let's learn about quantum mechanics. Quantum mechanics is the second major theory of modern physics. Quantum mechanics deals with very small objects, namely subatomic particles that make up atoms. Now that statement doesn't make much sense. Subatomic particles that make up atoms. The word atom means something that cannot be divided. That's what the word atom means. It means something that is so small that it itself can't be divided. It is the basic building block of everything else. That's what atoms were originally believed to be. Now we're talking about particles of atoms, which as far as our language is concerned, doesn't make any sense. For there to be parts of something, it must be divisible. But the word atom means unable to be divided. So I want you to see that there are some confusing ideas in modern science that really need to be examined carefully. If there are particles that are smaller than atoms, out of which atoms are made, then there's really no such thing as atoms. And that's an important problem to consider. Anyway, quantum mechanics as a theory deals with very small, that is, subatomic particles that may make up atoms. Atoms are the smallest units of elements. However, atoms are constructed of even smaller subatomic particles. Notice the apparent confusion there. Atoms are the smallest units, but they're made up of something smaller, such as protons, neutrons, and electrons. And just because we can talk about these things doesn't mean they're actually true. We've got to demand evidence if this is going to be science. Quantum mechanics strives to describe the properties and behavior of these and other subatomic particles. Often these particles, parts of atoms, do not behave in the ways that are expected by the classical physicists who are talking about things we actually observe. One reason for this is that they are small enough to travel at great speeds near the speed of light. At particle colliders, such as the Large Hadron Collider on the France-Swiss border, particle physicists can make subatomic particles travel at very high speeds within a 17-mile-long superconducting tunnel. We can see this tunnel here. They can then study the properties of the particles at high speeds as well as collide them with each other to see how they exchange energy. This has led to many intriguing discoveries, such as the Higgs boson particle, which gives matter the property of mass, and antimatter, which causes a huge energy release when it comes in contact with matter. Now, again, notice this is very confusing stuff that you are not expected to understand. But what you should understand is that these are things that are being discussed and studied by modern scientists who are following the assumptions and ideas of quantum mechanics, which is a part of modern physics. Physicists are currently trying to unify the two theories of modern physics, trying to unify relativity and quantum mechanics into a single comprehensive theory called the relativistic quantum mechanics. So we've looked at the history of the development of physics, and the author says physicists are currently trying to unify the two theories of modern physics into a single theory called relativistic quantum mechanics. So this gives us an idea of what's going on in physics today. Relating the behavior of subatomic particles to gravity, to time and space will allow us to explain how the universe works in a much more comprehensive way, hopefully. So in that section there, getting back up here, we looked at physics, past and present, and looked at the different ideas of physics. We saw ancient physics from ancient times to the Renaissance. We had ancient physics. Then we had classical physics from the time of the Renaissance to the 19th century, and then modern physics from the 20th century onward, which is represented by the theories of relativity and quantum mechanics. Okay? So that's that section there on physics, past and present. And that brought us up to the present state of modern theory in physics. Now let's look at another section titled Applications of Physics. And we'll read through this a little more quickly. You need not be a scientist to use physics, even though much of what we have been talking about is very, very scientific. You need not be a scientist to use physics, especially classical and ancient physics. On the contrary, knowledge of physics is useful in everyday situations as well as in non-scientific professions. This is one of the reasons why when I was a high school student, I enjoyed studying physics because it was useful and interesting. For example, physics can help you understand why you shouldn't put metal in the microwave, or why a black car radiator helps remove heat in a car engine, and why a white roof helps keep the inside of a house cool. The operation of a car's ignition system, that means when you turn on the key and it causes the engine to start, as well as the transmission of electrical signals through our nervous system in our body, are much easier to understand when you think about them in terms of the basic physics of electricity. Now, remember, electricity wasn't really studied until the 19th century. So that means that all of the time before that in history, these things are said to not really be understood, like our nervous system. If understanding our nervous system depends on a knowledge of electricity, then it would never have been possible to understand the nervous system until scientists began understanding electricity. And sometimes I think when scientists come up with new theories and develop new ideas, they sometimes think that those new ideas are now the explanation for everything. And so we've got to be careful that we don't allow modern ideas to become to be treated like they're the new explanation for everything, and no one understood this before, and now we understand it because there's some new discovery. You'll see scientists do this all the time. Physics is the foundation of many important scientific disciplines. For example, chemistry deals with the interaction of atoms and molecules. So physics is useful for the study of chemistry. That's why in high school, we study physics before chemistry. Not surprisingly, chemistry is rooted in atomic and molecular physics. Most branches of engineering are also applied physics. In architecture, physics is at the heart of determining structural stability, that is, the strength of buildings. Acoustics, how sound travels in buildings. Heating, lighting, and cooling for buildings. All of these things have to be considered by the engineers and architects who design and build buildings, and it's all dependent upon principles of physics. Parts of the study of geology, which is the study of non-living parts of the earth, usually we think of stones when we think of geology. The study of geology relies heavily on physics, including radioactive dating, earthquake analysis, and heat transfer across Earth's surface. Indeed, some disciplines, such as biophysics and geophysics, are hybrids or combinations of physics and other disciplines. And a discipline is a field of study. Physics also describes the chemical processes that power the human body. Physics is involved in medical diagnostics, such as X-rays, magnetic resonance imaging, which we call MRI exams, ultrasonic blood flow measurements. Medical therapy, physics also has many applications in biology, the study of life. For example, physics describes how cells can protect themselves using their cell walls and cell membranes, which you may have learned about or should have learned about in biology. Medical therapy sometimes directly involves physics, such as in using X-rays to diagnose health conditions. Physics can also explain what we perceive with our senses, such as how the ears detect sound or how the eye actually detects color. So all of these studies, all of these different sciences, they all in some way depend on physics. We might consider physics to be the science of all the sciences. We then have an example here, sort of a historical study of the travel of a satellite, a spacecraft that was able to reach a comet. I'm going to skip that and leave that for you to study if you're interested. And that brings us to this set of questions at the end and the quiz, which leads us to the end of this study. So we've come to the end of section 1.1. We've gone through, we've read all the content of the lesson. Um, what I would like you to do now is review the lesson, make sure you understand everything that we've studied, and then when you feel pretty confident that you know the content, I'd like you to go ahead and take the quiz for that first section. The quiz includes these questions here, so you might want to read through these questions first and think about the answers, maybe even answer the questions based on your lesson and then go take the quiz. And when you can do that and pass that first quiz, I would encourage you to go for 100% on that first quiz. Then you'll be ready to move on, and we'll get into the second section of Chapter 1 and study the scientific methods. Now, I know this was a long video. We read every word and every line, talked about the content of the lesson. I tried to help you see some of the controversial issues in the study of science that I encourage you to think about critically, because as a Christian scientist, as a Catholic scientist, we have lots of other ideas that we're committed to. We believe certain things, and we've got other sources of information that we rely on, like divine revelation, the authority of the church, the testimony of prophets and apostles and saints who have lived before us. So there's a lot more information to be considered than just what appears to be true based on our own limited experience. So there are bigger philosophical questions to ask in modern science, and I want to make sure that you feel comfortable asking those questions as we study the modern natural sciences. So I'm going to stop there for this lesson. I hope that it's helpful. I know it can be long. I know it can be boring to go through these videos, and very few students will make it through them. But I hope that by me doing the work of driving you through the chapter, it can help you to get through all of the content and really appreciate everything that our textbook offers, and also that I can help you to think about it from a Catholic perspective, because I think that the best and the truest scientists will be Catholic scientists. And we've got to hold people accountable who call themselves scientists, but don't actually speak scientifically. We've got to hold them accountable. We saw science defined in this lesson, and we've got to make sure that when anyone talks about science, they observe the rules of science and stick to the limits of science. I hope that's helpful. If you have any questions about this lesson, if there's anything you'd like to talk about, feel free to get in touch with me anytime. Once you're through your quiz and we're ready to move on, we'll get started in section 2 and study the scientific methods. I hope that's helpful. God bless.